11 people went to work on a Tuesday and never came home. The platform was considered state-of-the-art. On April 20th, 2010, the Deepwater Horizon drilling rig exploded in the Gulf of Mexico. The blowout that followed released approximately 4.9 million barrels of oil into the ocean, the largest accidental marine oil spill in recorded history. But here is what the headlines rarely explained. The explosion was not caused by a single catastrophic mistake. It was caused by a system, a layered, interconnected web of engineering assumptions, corporate incentives, regulatory gaps, and operational decisions that had been quietly failing for years before anyone noticed. This documentary asks one question: what hidden weakness inside that system made the Deepwater Horizon disaster not just possible, but almost inevitable? By 2010, deepwater drilling had become one of the most technically ambitious endeavors in human history. The Macondo prospect, located roughly 40 miles off the Louisiana coast, sat beneath nearly 5,000 feet of water and then another 13,000 feet of rock and sediment below the seafloor. Reaching oil at those depths required engineering that barely existed a generation earlier. BP, one of the world's largest energy companies, had contracted Transocean, the world's largest offshore drilling company, to operate the Deepwater Horizon rig. Halliburton was contracted to handle cementing operations. These were not inexperienced organizations. They were industry leaders working at the frontier of what offshore drilling technology could achieve. The public trusted them, regulators largely trusted them, and for years, the system had produced results. What few people outside the industry fully understood was how much that system relied on assumptions rather than certainties. Deepwater drilling operates under a principle sometimes called defense in depth, the idea that multiple independent safety systems exist to catch failures before they cascade. If one barrier fails, another holds. If two fail, a third catches the problem. The critical final barrier in this system was the blowout preventer, or BOP. A blowout preventer is a massive piece of equipment, in the case of Deepwater Horizon, weighing approximately 300 tons, positioned on the seafloor at the wellhead. Its job is simple in theory. If pressure in the well becomes uncontrollable, the BOP seals the well and prevents a blowout. Investigators later determined that the BOP carried design vulnerabilities, including concerns about its blind shear rams, that the industry had not adequately addressed. Post-incident forensic analysis suggested these were not isolated problems confined to this rig alone, but reflected broader gaps in blowout preventer design standards across deepwater operations. But the BOP was not the only weakness. It was the last one. To understand what went wrong, investigators needed to trace the decision-making chain that preceded the explosion. The Macondo well had been a problem well from early in the drilling campaign. In the weeks before April 20th, it had presented repeated pressure kicks and unexpected variations that required careful management. Warning signs had accumulated, but within a system that had normalized managing difficult wells, they did not trigger the response they deserved. On April 20th, the crew was in the process of temporarily abandoning the well, a standard procedure involving the removal of drilling mud and its replacement with seawater, reducing the weight holding potential pressure below in check. Before that process could be completed safely, the well's integrity needed to be confirmed. That confirmation came through a negative pressure test. According to the National Commission on the BP Deepwater Horizon oil spill and offshore drilling, personnel conducted the test on April 20 and misinterpreted the results. Investigators concluded the well was not secure, but those conducting the test believed it was. The uncomfortable truth was this: the results were ambiguous, and there were no standardized industry-wide procedures for interpreting them. The people on board reached the wrong conclusion using methods the industry had never formally agreed upon. That single misreading removed the last human decision point before disaster. Shortly after 9 p.m. on April 20, 2010, hydrocarbons, gas and oil began surging up the wellbore. The well was blowing out. Gas reached the rig floor and almost immediately ignited. 2 explosions followed in rapid succession. 11 workers were killed. 17 others were injured. The Deepwater Horizon burned for approximately 36 hours before sinking to the seafloor. The blowout preventer, the system's final safeguard, failed to seal the well. Oil began flowing freely into the Gulf of Mexico. It would continue for 87 days. The investigation that followed was one of the most complex engineering and regulatory inquiries in American history. Multiple bodies conducted parallel investigations: the National Commission appointed by President Obama, the Joint Investigation by the U.S. Coast Guard, and the Bureau of Ocean Energy Management, Regulation and Enforcement, and extensive litigation that produced millions of pages of internal documents and testimony. What investigators uncovered pointed somewhere unexpected. The evidence did not reveal a single rogue decision or a single point of technical failure. Instead, it revealed a system structured in ways that made catastrophic failure more likely than anyone had publicly acknowledged. Investigators began with the question every inquiry starts with: what was the last thing that could have stopped this? The answer led them to the cement. Pre-job modeling had indicated the cement slurry design used at the base of the Macondo well was likely unstable, results that, according to the National Commission, should have prompted serious concern before the cementing operation proceeded. A failed cement barrier allowed hydrocarbons to begin migrating upward through the wellbore. The well design itself had also reduced the number of physical barriers between the hydrocarbons and the surface. Decisions the National Commission found were made in a context of significant schedule and cost pressure. A pattern investigators noted reflected broader industry culture rather than isolated individual choices. And then there was the blowout preventer. Post-incident forensic analysis determined that the blind shear rams had not fully closed. The drill pipe had buckled under pressure and was off-center in the wellbore at the critical moment, preventing a complete seal. Investigators also found evidence that hydraulic pressure to the BOP may have been compromised. Every barrier had failed, not randomly, but through interconnected weaknesses that had never been stress-tested together. The National Commission's conclusion was direct. This was a story of systemic failure, an industry operating under insufficient regulatory oversight, inadequate safety standards, normalized risk tolerance, and diffused accountability spread across multiple contractors and operators. 11 families lost someone. That fact belongs at the front of any accounting of what the Deepwater Horizon disaster cost. BP's total costs, spanning cleanup operations, criminal fines, civil penalties, and legal settlements accumulated across years of litigation, ultimately exceeded $65 billion. Its 2015 settlement with the U.S. Department of Justice, valued at approximately $20.8 billion, was described at the time as the largest environmental settlement in U.S. history. The Gulf Coast fishing and tourism industries suffered damage that lasted years. The disaster also exposed a fundamental gap in regulatory capacity. The Minerals Management Service, the agency responsible for overseeing offshore drilling, had long been criticized, and the National Commission itself concluded that overly close relationships with the industry it regulated had compromised its effectiveness. The agency was subsequently dissolved and restructured into 3 separate bodies. The investigation changed offshore drilling in measurable ways. New regulatory frameworks introduced stricter well control standards, mandatory independent third-party verification of safety-critical systems, and significantly improved BOP design and testing requirements. The industry established new shared organizations focused on emergency response and well containment, capabilities that had not existed before April 2010. But the deeper lesson was harder to regulate. The assumption that multiple independent barriers would always hold, that defense in depth was sufficient, had been replaced with a harder question. What happens when the barriers are not actually independent? When cost pressure, schedule pressure, and organizational culture quietly connect them, a failure in one becomes a failure in all. What happened next changed how engineers, regulators, and risk managers think about certifying complex systems operating under extreme conditions. The Deepwater Horizon disaster is remembered as an environmental catastrophe. It was. But it was also a demonstration of what happens when a system is trusted more than it has earned. Every organization involved was experienced. Every piece of technology had worked before. Every individual made decisions that seemed reasonable within the information and culture available to them. That is precisely what makes the case matter. Complex systems do not fail only because of reckless people. They fail because structural weaknesses remain invisible until the moment they converge. They fail because warning signals are ambiguous. They fail because accountability is distributed across so many actors that no single person ever sees the complete picture. The question the Deepwater Horizon investigation ultimately leaves behind is not what went wrong on April 20th, 2010. The question is, which systems operating today are carrying the same invisible weight, and who is responsible for finding it before it breaks? Which industry do you think is carrying hidden systemic risk right now, and what would it take to find it before it fails? Leave your thoughts below. And if you want to keep exploring the hidden weaknesses inside complex systems, in technology, engineering, finance, and beyond, subscribe to Null Theory. Because the system is always the story.